Okay, this will be part 4. This is the fourth and last part of these large videos that cover chapters 7, 8, and 9, which is a huge part of Unit 2. There's only one other chapter which we'll cover separately, chapter 10, which is about straightening data. So let's pick up where we left off and we'll finish the notes today. Again, I'm going to share the whole screen so we can move back and forth between different things. Okay. So the first thing is, I just want to emphasize the difference between the slope and the correlation coefficient on a scatter plot, okay? This is something that once you work with a lot of problems, this becomes second nature, but at first it isn't sort of intuitive. So the slope B in the LSRL, that's related to the slope of the LSRL, right? So like you could have data that's tightly grouped positively, you know, if you have it's going up like at this rate, the slope, right, is higher here than it is here, right? Because it's about the slope of the line, right? So the slope is about the slantiness of the line. And slope is positive if you have a positive slope, negative if you have a negative slope, of course, right? The steeper the LSRL, the more negative the slope is, right? So the slantiness of the line is slope, right? But correlation coefficient is a measure of how tightly grouped the points are around the line, and you can have any R associated with any B. So if I have 3 examples of positive slopes here, right? But what the R is telling me is how closely grouped the points are to the line. So an R of 0.4 might be fairly spread out, right? An R about 0.7 would be closer. An R close to 1, the points are almost on the line, okay? And really the only connection between the two that seems apparent is that the signs are the same. So when the slope is positive, R is positive. And when the slope is negative, R is negative. That is true. But other than that, you can have, you know, any slope and any R being mixed. Okay, just the signs have to match. All right. Now turns out there is a connection. There's a formula actually that connects the slope and the correlation coefficient. And we're going to introduce a little bit about that here. I'll explain a little bit where it comes from. This is kind of a deviation to show derivation for those that want to understand where formulas come from. But we won't use this super much. If you have data, like the step height data, where you have the actual data for X and Y's, and you standardize this, I mentioned this in a previous video, then the point in the middle here at the mean X, the mean Y, which is called the centroid, X bar, Y bar, would have a z-score of 0 in both directions, right? And then you could take every data value and take the difference in the X from the X mean divided by the standard deviation of the X's, and then the Y's to find the Z in the X direction and the Z in the Y direction. And when you do that, you get an LSRL, which looks very much the same as the LSRL for the original data. It's just going through the point 0, 0, okay? All right, so LSRL shape is the same. When we standardize data, it changes the units, right? But it doesn't really change the shape of what's going on, all right? Well, it turns out that if you look at the slope of this line is connected to, let's see if I've got my notes for how to explain this most succinctly. Yeah, I don't. So the slope of this line is just related to the ratio of the z and the zy and the zx. So if I was on this point and I go out to this other point, then this z in the x direction and this z in the y direction to that point are related by the slope, right? The slope would be zy over zx, right? So you can kind of relate the slope to the z-scores to any point that's on the LSRL, if it was on the LSRL, right? But what would that look like if you wanted to take that back to the original data? Well, basically the idea is everything is shifted, right, because of the centroid. That's this part here. The other thing is that the z-scores, to get back to the original data, you have to multiply by these standard deviations. So when you do that, you end up getting this equation right here. It turns out that you can show that's proved, and I know I didn't really explain it fully on that last slide, but it's sort of a justification for why this is true. The slope of an LSRL is equal to the correlation coefficient to the data times the standard deviation of the y's divided by the standard deviation of x's. Okay, so now if you want to know more specifically, other than that little super quick introduction I just did about why this comes from, I actually have a full derivation PDF that can show that to you. So email that to me, or I'll show you where that is on the mrfeltling.com site later. But what we're going to talk about now is that this equation provides us a third way to write an LSRL. If we have some of the data but not the full data set, but nobody has run software analysis for us. So in your notes, or in your practice packet, I have 3 problems that are different ways to use this equation, and we're going to go through all of these. I'm going to switch to the practice packet to actually do the work, to have more data. So this first one, number 1, it says, what if we were not given the data set, but we were given the summary statistics, like the mean and the standard deviation of the x variable and the y variable and the correlation coefficient? Could we still find the slope in the LSRL? So we don't have software, so we can't copy it from a table. We don't have the data set to plug in, but it turns out we still can find the LSRL. And here's how we do it. First of all, we use the formula to calculate B. So we know B on that formula is RSY over SX. And so in this case, the correlation coefficient is negative 0.8734. And the standard deviation of the y, so we have to pick what we're doing here. We're going to stick with steps are the y variable and height is the x variable. Then the standard deviation for the steps is 4.9598, and the steps one is 3.2527, and the standard deviation for height would be 4.9598. And if you plug that in a calculator, you end up getting that the slope is negative 0.5728, okay? So we can find that way, okay? And that means that I already know that my LSRL is going to be y hat equals some currently unknown a. Well, here's the general form for an LSRL. We need to find these 2 things, but now I can go ahead and plug in my slope, or I can plug in my slope for the b. So use the formula to calculate the slope and plug it in. And that means I still have a left to go. So there's one more thing that you need to know, and that is, let me switch back to the notes for a second. In an LSRL, the LSRL will always go through this point, right? The centroid is always on the LSRL. And I also have a derivation that shows why that's true, if you're interested in knowing why that's true. But we're going to accept that as a fact. And what that means, if I go back to the problem we're working, is that I have one point that's on the line, right? I know the centroid, which is the mean x, mean y, which in this case is the mean of the x's is 4.9598, and the mean, the mean of the x's is the average height, 65.83333, and then the average y's is 16.139. That is on the LSRL, right? So what that means is if I plug these values in for x and y into this equation, I can solve for a. So I'm going to take that equation and plug in for y. I'm going to plug the average steps data. So that's 16.1389. Then I have my unknown a that I still need to find, minus 0.5728, and I'm going to plug in the average for the x, because that point I know has to make this LSRL equation true. And then you can just use algebra to solve this and get that the a turns out to be 53.8482. And now I have my full LSRL, so I can write it for real. Y hat equals 53.8482 minus 0.5728x, where x is the height and y is the number of steps. Right? So we have a way to write an LSRL if we only have the summary statistics. We just need this formula to calculate the b to get us started, and then we have to know that the centroid is on the LSRL. Okay? So that's one clever use of this, this formula. Okay, the next one in your practice packet is another one I want us to work together, and it's another use of that equation, which is, if we're given a data value standard deviation in x, could we find the corresponding standard deviation in y? Okay, so here's the justification. Let's say if a student's height is 1.2 standard deviations above the mean height of the class, how many standard deviations above the mean would you predict the student's number of steps to be, right? All right. So, so since we're talking about standard deviations, that means that the standard deviations for both x and y are 1, right? Whenever we standardize to z-scores, we always have 1. So if I start with that equation, which is b equals r sy over sx, that means that since sy and sx are both 1, b, this is just 1 and this is just 1, b is equal to r. In other words, the slope is equal to the correlation coefficient. Right, so they told me that the correlation coefficient for this data was negative 0.8734. So that means that my slope is negative 0.8734. Okay. And another thing you can look at is, you know, if you had the standardized score, remember we said, I went back to this in the notes. Let me go back to that for a second to show you. We said that if I went from the centroid to any point on the LSRL, that slope could also be just the z in the y direction over the z in the x. So using that fact, that means that the slope also has to be zy over zx. And so zy over zx has to be negative 0.8734. And so if I'm 1.2 standard deviations above the mean, which means z for the heights, the x's, is positive 1.2, I could plug it in this equation. Zy over 1.2 has to be negative 0.8734. And therefore, zy is that 1.2 just multiplied by the correlation coefficient. So 1.2 times that turns out to be negative 1.048. Okay. So what that's saying is, if a student here, x, this is the heights, right, x, and y is the number of steps. So we have a student, right, who is 1.2 standard deviations higher than the average. So there's some average height here, okay, and there's some average steps, right. Here's the centroid here in the middle. So I have a student, and that student is 1.2 standard deviations higher than average, right? Okay, they're somewhere here, right? So what we're saying is they're not going to be 1.2 standard deviations above the average steps. To get that, we have to take that 1.2 and multiply it by the correlation coefficient to know that it's, first of all, negative, and we only go 8/10 of the way down. So they're 1.2 standard deviations above the average height, but they turn out to be 1.048 standard deviations below the average steps. So you can kind of just think of it this way. In fact, some people find it easier just to memorize another equation. Zy is r times zx. You can just memorize that if you prefer, right? That if you have the number of standard deviations in the x, you just have to multiply it by the correlation coefficient to find the number of standard deviations in the y. All right, that's the second thing that we can do with this equation. I mean, it's based on that equation. And the third thing we can do that's unusual with this equation is we can determine the LSRL if we swap the x and y's, because we're not going to have the same LSRL. Like, let's say we had our original height, steps versus height data, and we had this LSRL here. What would happen? What would the new LSRL be if I wanted to swap the heights and the steps? Well, the grouping is not going to change, right? The new line is going to be a different slope, right? But it's not like the points change their grouping around the line. They're just as tightly grouped. So the R does not change, right? That's a measurement of the association, and swapping x and y has no effect on that. But does the slope change? Yes, it does. So before the swap, right, we have b is, according to that equation, r sy over sx. So after the swap, if I swap x and y, the new slope is just going to be that same correlation coefficient, but I have to make this sx over sy. I have to swap the x and y. All right, so here's how we do this. I like to kind of work with the original equation over here. Let's work with the original equation. We know that the original slope, we had y hat equals 53.846 minus 0.5728x. So the first b, I'm going to call it b1, is negative 0.5728, okay? Okay, but I know that this equation has to be true. So that b, that negative 0.5728, has to be equal to r times sy over sx. So negative 0.5728 has to be equal to the correlation coefficient, which we know is 0.8734, times sy over sx. Okay, so I'm going to stop right there because I don't want to go any further. But what I'm going to switch to is now the other equation. In the other equation, the new equation with it swapped, okay, I'm going to have an equation there, right? And I know that the slope over here, which I'm going to call B2, is rsx over sy, okay? And I know that the correlation coefficient is still negative 0.8734. That didn't change. But I need some number to plug in for sx over sy. Well, that's where we're going to solve over here. I'm going to do some more work over here. If I divided both sides by this decimal, I would get negative 0.5728 over negative 0.8734 is sy over sx. Therefore, sx over sy is just this fraction upside down. Negative 0.8734 over negative 0.5728. And that means that for this, I can substitute this in. So that's what I'm going to do. I'm going to put the sx over sy for the original in here. That's negative 0.8734 over negative 0.5728. And that's going to allow me to calculate the b. Right? So let me do that. If you calculate that in a calculator, you get that it's negative 1.332. Okay? And that means that my new equation here, which now has the height as the y variable, is going to be some unknown a, and then the slope now is 1.332, and then now we have steps in this location instead of the original steps height ordering. Okay? To find the a, we have to plug in the average for height and the average for steps, right? So the average height turned out to be 65.8333. Plug that in for that. 1.332 for the slope, and then the average steps is 16.1389. When you solve this, you get a turns out to be 83.3343. And so this equation, where we have height as the y, is going to be 83.3343 minus 1.332 times the number of steps. Okay, so this is another use of the equation that the b is r sy over sx. If you have to swap x and y, you just swap the x's and the y by finding the fraction, flipping upside down, and getting a new slope for the new line. Okay. So I realize these are pretty challenging calculations. That's why we're practicing them. Okay, at this point, I usually have people work in groups and complete this, but because this is going to take a long time and there's another topic, I'm going to ask you instead to pause the video, try working this problem completely, okay, and then go look in the posted solutions and see if that matches. And we're going to go ahead and go on with the next topic and the last topic in the class, okay, in the section. Oh wait, it's not the notes. Let me go to the notes. Okay, so we just went through those things. And typically at this point, we would do the ticket price versus distance problem. I'm not going to do that in this video. But I do want to highlight that that means that now we've covered 3 different ways to find the equation of an LSRL. If you have the full data set, you can use your calculator. You know, enter the data, run linear regression. If you have the output of software, you can use the table, right? If you have no data or software, but you have the summary data, you need to have the correlation coefficient and the mean of the x and y and the standard deviation of the x and y. Then you can use the method we just did in problem 1. So there's 3 different ways that you can use to find an LSRL. Okay? All right. The last set of topics here has to do with the effect of outliers. We said that correlation and slope can be very much affected by outliers. So let's talk about that a bit. First of all, There's a concept called leverage, and we know that whenever data is not, so first of all, what is an outlier? Let's just first define that. An outlier for two-dimensional data is defined as points that are not following the pattern. So the word outlier here means points not following the general pattern. Okay, so that's the first thing. Definition of an outlier, a point that is not following the pattern. Okay, so what effect does it have? Well, let's take a look at something. I'm going to see if I can find this online, because this is helpful if it's still operational. Yes, okay, good. All right, so let's say that I have some data points here, okay? And I have the centroid of the data right there. And the LSRL is going through that, and the LSRL is kind of going through the data, averaging the residuals. Okay, what would happen if I moved a data point around? Okay, so let's take this data point out here. Okay, if I move it along the trend, then it doesn't have any effect on the line, right? Because it's still matching the pattern. But if I move it off the trend, okay, and I'm way out here, then moving it around has a very large effect on the slope. In fact, even though it's only 1 point compared to these other 4 points here, it basically determines the whole slope. Like if I put it kind of in line with the rest of the points, the slope stays positive, but if I move it down here, just this 1 point can force the whole LSRL to be negative. The slope will be negative, right? Now, if I move it closer to the centroid, like I put it directly over the centroid, and then I move it up and down, it doesn't change the slope at all, right? So it's almost like this LSRL is like a seesaw. That's the pivot point is the centroid. You can cause a data to move up and down a little bit, change the y-intercept over here. But for it to move the slope around, it has to have leverage. It has to be out here so that it can twist the line, right? And if I had it over here, it would twist the line this way. So what happens when points are outliers in two-dimensional data like this is that if they're far enough away from the centroid horizontally, so they have what we call leverage, this distance this way, then they will tend to pull the LSRL to themselves, okay? The same thing over here. They'll tend to pull the LSRL to themselves, okay? The farther away they go, the farther away they are horizontally from the centroid, the bigger effect they have, okay? So we can kind of summarize that with these graphs here. If you have a point that is way out here, like it has what we would call high leverage, this distance in this direction is very high. This is the leverage. If it has high leverage, but it's already following the trend, we would say it's not an outlier. It has a very small residual, and it doesn't have very much influence on the slope. So we would say it's not an influential point, or at least it's not influential on the slope. Even though it has high leverage, you have to have some residual compared to the existing pattern for it to push this line around or pull the line around. Okay, this data point over here has a high residual. It's definitely an outlier. It's not following the trend, but because it's right near the centroid, it has very little influence on the slope, right? Because it doesn't have enough lever arm. It doesn't have enough leverage, right? It will have some effect on the y-intercept, but not a huge effect unless there's a very small number of points. Okay, but a point out here that has high leverage, right? And it also has a residual compared to where the point would be if it wasn't included. It has a high residual there. Then it will tend to have a large influence. So it's very, what we say, very influential on the slope because of its leverage and its initial residual. Now, what's weird about this is when you include the point, it will tend to pull itself down and try to reduce its own residual as close to zero as possible. So if it has enough leverage, it actually will end up having a large residual. So the word residual, you have to be cognizant of, are you talking about the residual before I include the point or after I include the point? Because when I include the point, it will pull the LSRL to itself if it has enough influence on the slope. Okay, so that's the first thing is so points that are removed from the pattern only have effect on the slope if they are away from the centroid and they're not on the existing trend line. But if they have enough leverage and enough residual, then they will be influential on the slope. So we have to be cognizant of how that affects things. And then there's a separate effect that occurs on correlation. So Remember, the correlation is the average of the product of the z-scores. So the z in the x direction times the z in the y direction, right? So if you have a point like this, let's say, right now, I have basically most of my data is in this trend around this line. So this data point out here is far from, it's not following the pattern, right? And that means that effectively this weakens the correlation. So if this was a positive correlation, like let's do our kind of number line for correlation, weakening the correlation means it's going to move closer to 0. R is going to move closer to 0 because the points are on average further now away from where the rest of the data is. On the other hand, if you have data over here like this, where most of the data is in this region, and you add another point that's there, then that means that on average, the data is now a little closer on average to the mean because there's more data points close. So this will strengthen the correlation, and that means that the R value will go either towards 1 or towards -1, okay? But there's kind of two values where the two regions where the points have very little effect. They're kind of like dead zones, and that is right in the region near the average y value and right in the region where the average x value is. So in a little region here just directly above and to the right and left of the centroid, because in this case the z in the y direction would be about 0, and in this case the z in the x direction would be about 0, and this is the product, that data point will have very little effect on the correlation coefficient. So even though it's in a position to be able to weaken the correlation, there's a little dead zone here where the points have very little effect on R, small, if any, effect on R. It's just an affectation of the way the math works, okay? But mostly, we would just be cognizant of, on average, is the data now further away from the mean, which would weaken the correlation, or is it now on average closer to the line, which means that we're strengthening it. All right, a couple other things related to terminology, and then we'll be able to wrap up this large discussion on bivariate data. So first of all, very, very important point. Association does not imply cause and effect. Causation is another name for cause and effect, okay? Even if we have a very strong association, even if these dots were right on this line, it doesn't mean that changing the x variable will definitely cause a change in the y. And here's a good example to show you why. Let's say that I plotted the life expectancy. When people died, I looked at how long they were alive. And then I went back and asked the family, how many TVs did you have in your household? And I find that it just happens that people who live longer happen to have more TVs in their house, right? So does that mean that if I want to cause somebody to live longer, I can just give them some TVs? Is there some sort of a cause and effect relationship here? The answer to that is definitely not, right? I mean, we're not going to cause someone to live longer by giving them a television, right? So what's happening here? Well, what's happening is there's something going on in the background, right? There might be another variable, like let's say wealth, that actually is affecting both the x and the y variable. So if you have higher wealth, then you can afford to get good medical care, you have good medical insurance, you go to the doctor regularly, you probably eat well, stuff like that, and your life expectancy. So if wealth goes up, life expectancy probably goes up. And also, if you have more wealth, you probably have more TVs in your house. So even though it looks like these two things are connected, the real connection is there's sort of a puppet master back here, right? That's got the strings. And that wealth is controlling both life expectancy and number of TVs to make them look like they're moving together, right? So just because there's an association, no matter how strong, that doesn't mean there's a cause and effect relationship. Typically, the way we write this is well, typically it's written this way. Correlation is not the same as causation. So if you've ever heard that phrase, that's what this is referring to. All right, so we'd be careful to not imply a cause and effect relationship. We'll talk later about how you can in Unit 3, but we have to conduct something called an experiment in order to show that. And there's some very specific requirements that have to be met. So some terminology for you here. So one term that you may see is lurking variable. That is like this wealth variable. So if there's something in the back that's causing two variables to move together, that third variable, the hidden variable, is called a lurking variable. Our textbook uses it. It might appear here and there in the notes and problems, but that's actually not an official term. So for the most part, we won't use it very much. But whenever we have two variables where I can't determine their effects being different, those variables are called confounded variables. So let's say, for example, I'm measuring some sort of health outcome, okay? And it could be due to a medicine that I'm giving someone, but it could be that it just reacts differently depending on their age. If I don't control for those things, so I can't tell if I saw a change in outcome because of the medicine or because how young the patient was, then we would say these two variables are confounded. Now that is an official term, and that's used on the AP Stats exam. We'll cover that in more detail in Unit 3 when we talk about experiment design. Okay, the word association we know is a general meaning. That just means there's some relationship. That's an official term, but it's general. This is where we talk about an association being linear, strong, and positive, or something like that, right, in general terms. The word correlation, AP, that's an official term. It's used on the AP test, and it specifically means the correlation coefficient. So the word correlation means correlation coefficient. So if you don't mean R, you should use the word association, okay? And then we have some standardized wordings that I want to include in the notes here. You should basically memorize all these standardized wordings, because if you want to get things right on the test and on the AP exam, these are the wordings that we know work and that they will grade highly. And they're also great ways to express things. So if you're talking about slope, you should use wording like this. For every 1 added inch in height, the number of steps decreases by 0.57 steps on average, right? In other words, for every change of 1 unit in X, Y changes a certain amount, but in context. For intercept, you can use wording like this. A person who is 0 inches tall is predicted to take 53.8 steps on average, something like that. If we're talking about association or explaining the meaning of R, then we would say, okay, there's a linear, negative, fairly strong association. We have to include something about the direction, right? The strength and the shape, the form of it, okay? In context, always in context. Explaining R squared, we saw, was about explaining the percentage of the Y variable that is explained by the model that links it to the X, but this is the wording that works well. Something like about 76% of the variation in the number of steps is explained by the LSRL, which relates the number of steps to height. And then if you want wording for explaining the standard deviation of the residuals, you could use something like this. The actual number of steps for a given height are 1.58 steps away from the predicted number of steps on average. Or you could say something like the average error between the actual and predicted number of steps for a given height is 1.58 steps. So some standardized wordings that we should be aware of. All right, and then I think that's it. All right, so 4 parts to cover this big thing. Lots of problems to practice with. And then we'll cover chapter 10 separately, which is the idea of when you have data that's not straight, we precondition it by transforming it, and then we do everything related to lines on that data. All right,